Hello, everyone. So I think you should be able to see my screen. So thank you, Bastian, for this nice presentation. So as Bastian said, I'm coming from University of Ljubljana. I'm also affiliated with the UNESCO Chair on Water-Related Disaster Risk Reduction, and today I will show you some potentially useful examples how to use R for hydrological analysis. So the idea of today's training is basically to show some examples how you can use R for basic spatial analysis, for simple rainfall runoff modeling, for low flow analysis, for flood frequency analysis, and for basic analysis like data import into R and plotting and so on. So everything together, it will be a bit too much for 45 minutes that we have. So I will just firstly do a brief introduction into these topics, and then I will switch to R code and I will briefly go through the R code that I have prepared. And at the same time, I will share with you my OneDrive link where you can download the code, the data example, and also this presentation, and you can then check the R code and some examples on your own and see if you have any similar data that you can use and so on. So in general, last year I also prepared, let's say, a workbook or tutorial that is uploaded to Zenodo, where you can get this tutorial. You can download it with some exercises, some solutions. So basically, this was prepared in R Markdown, so it has a shape like this. But in general, initially it was published like a Slovenian textbook, and afterwards it was translated in English. So this workbook does cover firstly the initial basic steps of how you can use R if you're not like an expert user, and then like in the chapter number 4, several different hydrology related topics are discussed and presented, how in some cases are shown how you can use it, how you can use R for different analysis. So also, as I said, the Slovene version is online. So if somebody is interested, this is also an option. So within this training session, we will assume that you already have some basic R knowledge. But in case you do not have it, so R is an open source and freely available statistical tool, software that provides a range of functions, packages for analyzing data, visualizing results, developing statistical and other models. So it's quite widely used in variety of disciplines, and it has, I think, more than 10 or 15,000 packages. And within these packages, you can find almost everything, almost all the different functions or code that was already developed by somebody else. So within today's presentation, I will be using RStudio. So RStudio is also, in general, to some degree, open, freely available. And it is basically a graphical user interface for R. So it does look like this. So the top left window is kind of text editor where you can write the code and store it, modify it, while the bottom left corner shows the console. So this is where the commands and calculations are executed. The top right corner shows like the environment, the history, so the previous functions that you have run and so on. And the bottom right corner shows the plots, the packages that you can activate, deactivate, the help page, and so on. So as I said, if you don't have any prior knowledge with R, I advise that you check the workbook that is available online. It's free. You can check it and go step by step and get more familiar with the software. So today I have prepared a sample or example of the data from Slovenia. So this is a combination of the discharge data and precipitation data, and also some evapotranspiration data calculations. So I have collected daily discharge, water level and water temperature data from one gauging station, and rainfall data from 6 different stations located within this catchment. And we will see later on within the R code where the stations are located and how you can use the data. And also a bit more information about the stations and everything is included in the R code. So if you want to get the data, so this is the link. I will also maybe just copy it into chat, so you can download it so that I will not forget. Just a second so that I can find the chat. Let me know if this is if it's not working, the link, but I think it should be working. So you can download the data, you can download the R code and the presentation as well from this link. So it is compressed into one RAR file, so you should extract it before use, of course. So yeah, as I said, different examples will be shown. So firstly, I will show how you can import the data from Excel, how you can do some basic plots, how you can aggregate the data from daily to monthly or from daily to annual data, and how you can do some simple water balance calculations and some simple plotting. Then for the spatial data, I prepared some simple examples how you can import raster and vector data using the Terra package, how you can reproject using R, how you can do some clipping, extracting of the raster data based on the shapefile, so based on the polygon extent of the catchment. And additionally, there is an example how you can calculate the aerial precipitation using the Thyssen polygons method in case that you have multiple stations located within the catchment. And there is also an example how you can download directly into R the satellite-based rainfall data. In this example, the CMORPH satellite data set is used to import it. And I will show how you can use it and compare then to the aerial gauge data from your catchment. For the rainfall runoff modeling, so an example will be shown using the GR4J model. So this is a French model developed by the French Research Institute in INRAE. So it's a relatively simple bucket type model that does a very good job in modeling the runoff in case of alpine or let's say also some continental catchments. And these models are also freely available, so you can download it. You can download them from this web page. So besides R package, there is also an Excel version of this model available, so you can even use it in Excel. And additionally, they also have more sophisticated models, like with with larger number of parameters and using also the snow module. And also they have the model with the hourly time step that can be used for flood forecasting and so on. And besides the basic package RGR, they also have the RGR teaching package that is basically a shiny web interface where you can uh, you can see it here also on the slide. So this is like you can change the buttons, you can change the settings, and you see how does the change of the parameter impacts the simulation. You can change the time window, you can run the calibration, so you can do everything, uh, all the steps interactively in our Shiny application. So it's very good for teaching, for example, if you're interested, of course. So this is the basic structure of the model that we'll be using, but I will not go into the details. So if you're interested, you can check the web page. You can also check this presentation. But as I said, the model is relatively simple. It does uses only 4 parameters, so the names are quite simple: x1, x2, and x3 and x4. It uses the production store and routing store, and then simple calculations also with using some kind of unit hydrograph theory. The input data is the precipitation and the potential evapotranspiration, and the main output is the discharge. So the daily simulated discharge is the main output. So these four parameters can also be represented graphically within the catchment. So you can see here what should x1 parameter x1 represent, what should x2 and x3 and x4 represent. And here is also a bit more detailed description about the main calculation steps of the model. But as I said, this is not really the aim of today. Today is more the aim to show some R code and some examples how you can use R. Okay, so if you're interested, you can check this presentation, upload it to my OneDrive or the basic INRAE webpage where you find all the code, all the papers and everything. As I said, so there are also more sophisticated models available. So as Nejc is the snow model that can be used together with the basic model. They also have the model with the 6 parameters, so adding one exponential storage here, which improves the low flow simulations and so on. So low flow analysis, some simple examples are also included in the R code. So these examples will follow the ELF-stat package, which was basically developed based on the manual published by the World Meteorological Organization. So the manual deals with low flow estimation and prediction, and this ELF-stat package is basically based on this manual. So the functions within the ELF-stat package support this manual. And at the end, I will also show the example how you can do the flood frequency analysis, how you can derive or how you can calculate the design discharge values in case that you have a sample of high peak discharges and you should fit different distribution functions. In the example that I will be showing, the method of L moments will be used, but of course any other method can be used for parameter estimation. Okay, so I think this was more than enough. I will now switch to R and I will briefly go through the code and try to additionally explain some of the steps that I will be doing within the presentation. Okay, so first thing, as I said, just a bit of repetition. So this window on the top left is showing the code. So this is what I have prepared before. So this is kind of notepad. I can add comments here. I can put the code into the comment and I can delete it, modify it, save it, and open it somewhere else. So here is the console. So here the calculations will take place. Here I have the environment. So these are my variables. You can see that I have many of them. So I have done some testing before and some additional calculations. In the history, you can see my previous functions that I have used. These connections and tutorial are not that interesting for a basic user. Then maybe packages. So here is my list of packages that I have installed within my R. So the ones where I have this check mark. So these are the activated packages. So I can always install new package by clicking the install button, typing the name of the package and then clicking install. So I can use different repositories. So the basic repository is CRUN. I can also download different packages, I don't know, from GitHub, for example, and install packages directly from GitHub using the zip or targz extension. And here I also have the help. So the help is in general structured in the same way for all the R packages. So this is help for function named seq, which is basically can be used for sequence generation. So for all the functions, the help is structured in the same way, meaning firstly you have some description, then some usage example, then the arguments are shown. So the arguments are basically kind of settings of the function or the input data. So in case of this function sequence, for example, the arguments are from, which means that this is the initial step of the sequence generation. Then you can say at the step, for example, I would like to have like number generated by the difference of 3, and I would like to go to the number of 15 or something like that. I can run the function and I will get the result. So always in RStudio, so the blue color indicates the input, and then this is the output of the function. So I have generated a sequence of 5 numbers with a step of 3. Okay, so then you have here in the help some details, and at the end, very useful, some references, and completely at the end, some useful examples. So if you are not sure exactly how the function works, you can always run the examples and you will see how it works, and you can then then you are able to modify, change the arguments, change the input data, and adapt it to your needs. Okay, so let's go to my example. So firstly here, you will see this is a function with which you can install the package. So this readxl is the package that can be used to import the data directly from Excel. So I already have this package installed, so I will just activate it. So this library readxl is basically the function that is needed to activate the package. And if I go here now under my package list, I will see that it is activated. So alternatively, I could also click just on the button and I would be able to activate it as well. So you have probably noticed that I put the part of the code from my notebook to the console. So you can always do this with clicking this run button or simply just pressing Ctrl plus Enter on your keyboard. So this is the same thing. So if you click the run button or click Ctrl Enter, this selected part of the code will be executed within your console. So you should be, of course, careful what you select. So for example, if you select something like this, you will get an error written in red. So the error basically means that something happened that R does not know what to do with it. And in this case, the error is related to the fact that I was just trying to put this part of the text, so these characters, into the code, and R did not recognize it as any familiar function or expression. Okay, so the hashtags do indicate the comments. So everything that appears after the hashtag is a comment. So if you run this into the console, nothing happens because R knows this is a comment. Okay, so using these 3 lines, I will import the data from Excel into R. So this is already a function. It does look quite complex, but there is also an alternative if you would like to import the data from Excel. So you can always go here into the environment, import dataset, select an option from Excel, and then you can browse for the file that you would like to export, and then you have here the settings. You can select which sheet you would like to export, what will be the name of the data set, how many rows to skip, what is the range that you would like to import, and so on. So you can play with this, and you have probably also noticed that there are also other formats where you can directly import the data using the RStudio, using this graphical user interface, so that you don't need to type in the code directly. Okay, so I will first transform the data into a data frame. And now if I check the structure of the data, I will see that I have 4,748 rows, which are the observations, and I have 15 columns, variables. So the first column is the date, then I have the water level, the discharge, water temperature, and so on. So here is a bit of description. What does every of the data of the columns means? What does they represent, and what are the units? So I hope that this will be useful to understand what the data is. Okay, but now let's move further on. So this function is also useful. So if you would like to check just the first 6 rows of the data, you can type in hat and you will get just the first 6 lines. Similarly, it is also sometimes useful to check the end of the data, so the tail. And in this case, you can see here that the data ends in the end of, so in the last December in year 2022, and the data starts in the 1st of January 2010. Okay, and the next step that I will do, I will convert the column with the dates from the character format. So here you can see that the date column was read initially by R as a character. And if I would like to transform this into a date, I can use this function as date. I need to tell what is the format of the date. So in this case, this means day, dot, month, and year. And in this way, I can transform it into date format. And now if I check the structure, you can see the difference. So you can see here, okay, R now knows this is the date, and then you can also do some additional analysis directly directly using dates. Okay, so summary will give you the basic descriptive statistics of every column. So you can see here, for example, for the discharge. So the discharge was given in cubic meters per second. So the minimum is 5, the maximum is 860, the average is around 40. So if you want to extract only or do the summary only of individual columns, so this squared brackets and C basically means that now I would like to extract only column 5 and 6 and do the summary on the column 5 and 6. So if I would like to extract only, let's say, element number 10 in columns 5 and 6, I can do it this way. So the number before the comma in the square brackets indicates the row, and the number after the column, the comma indicates the column. So this is the same thing in the same structure, meaning as it is used within the matrices. So if I want to have row 10 and row 11, this is how you can do it. Okay, I can also calculate standard deviation. So standard deviation of column number 3 or standard deviation of the discharge data. So the result here is the same. So this is basically equivalent. So using this type of extracting the data or the dollar sign and the name of the column, in this case, give the same result. So I can also do the simple plot. So plotting the discharge data. So on the x-axis, I would like to plot the date, on the y, the discharge. So if I would like to be more precise, I should do it like this. So to explicitly say, okay, this is on x-axis and this is on y-axis. And then I have the labels of x and y-axis, the type of the graph and the title of the graph. Okay, so you can see the settings. If you're interested more settings of the plot function, you can see it here. So the different types of the plots that are available and also all the arguments that can be changed within the plot function. Okay, then here is one example how you can basically interpolate, how you can estimate the missing data. So one of the rainfall stations have some missing data in between, and using simple linear model, you can estimate the missing data based on the correlation with the closest station. So I will not go here into too much detail, but if you're interested, you can check it out. But in general, the idea here is just to fit the missing data. Then if I want to calculate the correlation, Pearson correlation coefficient between the two data sets, in this case is between the first precipitation station and the second precipitation station, I can do it using the core function, and you can also use different correlation coefficients like the Kendall or Spearman correlation coefficient. There is also an interesting core plot package which enables you to do, let's say, nice or more nice correlation plot, something like this, that basically then you can see which stations have the strongest correlation. So in this case, you can see that the strongest correlation is between the station number 4 and station number 1. So Gornji Grad and Luce, while some other stations like Solčava and Laško have lower correlation. Okay, Then another package that I will be mentioning is the zoo package. The zoo is very useful for combining the dates with any variables or environmental data, and it can be used quite effectively together then with the aggregate function to very easily aggregate monthly, sub-monthly, annual, whatever type of data you would like to do and extract. So this is very useful in most of the hydrological applications. You always need to do some statistic or some summaries. Okay, so here I basically just combine the discharge data with the dates into a zoo object. So now I can also directly plot the zoo object. So you can see here that the plot is very similar to what I had before, just that now it's using directly the combine zoo object. You will see that this one has now the structure of zoo series that can be then used for further calculations, as I said. And in this way, with this example, I can then easily aggregate the annual sum of the discharge data. So in this case, this is of course not very meaningful numbers because the discharge initially had the units of cubic meters per second. So if I would like to have the sum of the discharge in millimeters, which is usually used within the hydrology as to do the water balance, I need to get rid of the seconds from the cubic meters in seconds. I need to divide then this number with the catchment area. So in this case, 1,847 is the size of the catchment area. So for this gauging station, and in the end, I need to convert it to millimeters. And if I do this, I will get the Q annual in millimeters, and I'm now able to see what was the runoff in millimeters in specific years. So I can see here that the year 2011, for example, was relatively dry, while the year 2014 in this catchment was relatively wet with a lot of runoff. Okay. If I now do simple average of 5 rainfall stations, so sum all the rainfall for all the days and just divide with 5 for all the rows, I will get the average rainfall for all the days. And if I repeat this exercise, so first create the zoo object and then aggregate it to get the annual rainfall, I will now get the annual rainfall. And now if I plot it, you will see that this is very similar pattern. So the most rainfall was measured in year 2014 and the lowest one was in 2011. Okay. And I can do the same here for the potential evapotranspiration. So in the example that is uploaded to my OneDrive and that I'm also showing, you have the last column is the calculation of the reference evapotranspiration using Feynman-Montis equation based on all the meteorological data available for this station. And you can see here which station this is. So this was done for Celje station. So this is a relatively big city in Slovenia. Okay, so you can do the same for the evapotranspiration, and if you do this, you can also calculate then, for example, the runoff coefficient. You can calculate the ratio between the reference evapotranspiration and the precipitation, and additionally, you can also compare the runoff calculated directly from the discharge data and the runoff calculated as a difference between the rainfall, the precipitation, and the reference evapotranspiration. And you can see here that in some years this does agrees quite well, but in some other years there is a bigger difference between these calculations. There are several potential reasons for this. Okay, so this is shortly a bit of introduction how you can do some simple aggregation of the data, some simple plotting. Okay, so about the spatial data, so the Terra package is, let's say, state of the art at the moment. It includes really a variety of functions that can be used to do all sorts of stuff that you would otherwise need to do in GIS software. So you can almost do everything within R that otherwise you can do with GIS. So for example, this code will just import the catchment boundary So the vect function is to import the vector type of data. And if you plot it, you will see this is the catchment boundary. And this geodata package can be used to download the elevation data, so the global data set. So in this case, I downloaded the digital elevation model of Slovenia. And if I plot it, you can see it here. So the elevation goes up to around 280 meters above sea level. And here in this lower left corner, we have the seaside. So the elevation here is 0. And if I check now the coordinate system of my catchment polygon, I will see that this is something that is in the Slovene coordinate system. And if I check it, sorry, this one was in the geographic coordinate, this one was in the geographic coordinates, and the one for the Slovenian catchment boundary was in Slovenian coordinate system. So I need to reproject. So R can also be used to reproject. So if I want to reproject the catchment boundary to have it in the same coordinate system as is my elevation model, I can now plot everything together. So you can see here the overlap between the digital elevation model and the catchment boundary. I can do the summary for example, digital elevation model, and I can also mask the catchment. I can crop it. I can calculate the slope, for example, of the entire Slovenia. I can calculate the catchment hypsometric curve. So this one tells you what is the percentage of elevation below and above specific threshold. So, and I can also do using the Terra package, I can also plot plot the points. So let me show this. So the 5 red points are basically the 5 precipitation stations that I have mentioned earlier. So here you will see that I have created a data frame with 3 columns. So the first one is the names, the second one is the longitude coordinate, the second one is the latitude. And then from this data frame, I can create, using again the vect function from the Terra package, I can create a vector format that is recognized by R. So this is spatial vector format that can be then added to the plot, and you can also extract the data and do all sorts of GIS-related analysis. So here I also needed to change the projection to the same coordinate system as is of the elevation model. I can also save these 5 points into a shapefile if this is what I would like to do, or I can calculate the Thyssen polygons. So this Voronoi function from the Terra package does calculate the Thyssen polygon methods. And if I do the intersection between the Thyssen polygons and the catchment boundary, I will now get, I then get, if I plot it, I can do it like this. I get the intersection with the catchment and the Thyssen polygon. So from this, I can calculate what is the area that is covered by individual precipitation stations. So one station, according to the Thyssen polygons methods, is covering 160 square kilometers and so on. And now I can use this to calculate the aerial precipitation with the consideration of these weights of the Thyssen polygons. And I can aggregate it the same way as before, and I can plot it, and you will see that in general the pattern is similar as before. Just the results are slightly different and should be slightly more accurate because I have considered the weights, so the weights calculated from the Thyssen polygons for each individual station. Okay. So the following code, the following example shows how you can use this p recipe function to download directly, in this case, the CMORPH. So the CMORPH is satellite-based precipitation estimates data. Let's do it. So this takes a few seconds to complete. And then with this Rust function, you can basically read or import the data that was otherwise stored in this folder into R. So if I plot it, you will see that I get this 2 times square brackets means that I plot the first data. So this one is basically giving you the annual CMOR precipitation estimates from 1998 till 2021. And what I have plotted is the annual rainfall data for the whole globe using this from the CMOR satellite-based estimates for the year 1998. And now if I basically extract, so clip all the rasters with the catchment boundary of my catchment that I have using this for loop, uh, and I compare now the the data that I have from my gauges from Slovenia, so the red ones, with the CMOR of data in black, you will see that there's quite a big difference between the precipitation estimate based on the satellites and based on the actual gauge estimates in this catchment that has quite significant torrential characteristics. So in this case, the satellite is basically underestimating the precipitation. Okay, so the following example is showing how you can set up a rainfall runoff model that I mentioned, so the GR4J model using the RGR package. So these functions are a bit more complex. I think I don't have that much time to go too much into the details, but if you want, you can always check the help, or the easiest way is basically if you have your own data, then you can check the example, try to modify it with your code, and you will see what each argument represents, and you will more clearly understand um, what what specific function is doing. So much more information about modeling you can find in the tutorial. Here, just what I did simple calibration of this rainfall model for part of the period. So I think until the end of 2018 was used for the calibration. So data from 2010 to 2018 was used for calibration. And this is basically the result of the calibration. So in orange, you can see the simulated runoff, and in black, you can see the observed runoff. And you have different comparisons. So here is the 30 days rolling mean. Here you have the flow duration curves, and you have the scatter plot as well. And here you have the precipitation data. So in general, you can see that based on the fact that the model is quite simple, the performance is quite good. So adding the snow module or improving or adding more parameters to the model would even improve the performance of the model. Okay. Um, so the following example here in the R code additionally shows some low flow analysis. So basically, as I said, this is following the World Meteorological standard or manual for low flow estimation. So in this example, basically you will see that the function does extract the base flow based on the detection of the turning points in the discharge data. And based on the detected base flow, you can then calculate the base flow index, some low flow statistics like Q90, Q95, some seasonal indexes, and so on. And you can also, using this package, you can also plot the flow duration curve, either for entire period or for specific years. You can also then compare specific years. So you can see here that comparison, for example, between the flow duration curve from year 2014 and 2022. If you remember, so year 2014 was quite wet, so the flow duration curve is also much higher compared to the flow duration curve from year 2022, which was again a more dry period. So you can do this kind of simple analysis using this alpha-stat package. You can also You can also extract the drought periods based on the selected thresholds, for examples. And this alpha stack package also enables this interactive interactive plots that can be used to more in detail observe and check the data and all the results. Here in this case, the gray columns indicates the identified drought periods. You can see here, this is the period where the discharge was below the threshold that I selected here for identification of the drought periods. You can again do some simple aggregation of the droughts. You can see here what I did. So I counted the number of droughts in different times of the year, and you will see that since this is continental, or let's say alpine continental catchment, so most of the drought periods were identified in summer period. And if I use the different threshold, I get slightly different results in terms of the detected droughts. Okay. And here I can see what is in which days did the annual minimum flows occurred in specific years. So this can be also sometimes very useful. Okay, and the last example that is included in this R code is how you can do the flood frequency analysis. So as I said here, the method of L moments is used to fit the L moment based on a sample of maximum annual values, and then I think 5 distribution functions, so Weibull, normal, Pearson tree, generalized extreme value, and Gumbel are fitted to this sample, and then you can basically do simple plots or calculate simple quantiles for different return periods, and you see what is, for example, the design discharge for specific years. So adding the measured data as well to the plot, you see that the sample is quite short. The reason is that I only had 13 years of data. And you see that some distributions, like normal distribution, does underestimate the design discharge values, while for example, the best fitted in this case is probably the GIV. And from this, then you can estimate, for example, what would be the 20 years return period or 25 years return period. And the last example is basically you can also calculate the confidence intervals based on considering all the uncertainties in the sample, and you can get these dotted lines indicate the confidence intervals, which can be also sometimes very useful. So here, before I end, I have a final remark. So this example is done based on maximum of the daily discharge data, while this is not really okay for the torrential catchment that I have been using. So I should be used like the actual peak discharges, so not the daily values, because in torrential catchments you have quite big difference between the actual peak discharge and the daily average value. So in this case, the plot that I'm showing here is like probably significantly underestimating the design discharge values. So, but I just didn't want to confuse you with additional subset of the data from the hourly or sub-hourly data and then extracting the peak discharges. So that's it from my side. So maybe a few concluding remarks. So I have shown some practical examples how you can use R. So I know that this was super fast. I tried to do like a brief introduction of every of the 5 or 4 different topics. So if you are interested to go more into detail, you can check the code and then go to the tutorial, to workbook. Then you will find more detailed description, more examples, and also some tasks that you can try to solve. And additionally, on Zenodo, there is some there are the solution of the tasks that you can use to double check if you did it correctly. But of course, sometimes in R you have different paths to the final solution. So there is most often not only one solution, but there are more solutions. And using different models and everything, just a final remark. So you should be always aware of models limitations and the corresponding uncertainty. Okay, so that's it from my side.